Hi, hello everybody. This is a topic on crystallization in foods, and in this lecture I will discuss about the first stage in crystallization, which is nucleation. But before watching and listening this lecture, I would suggest you listen to the previous lecture, because in the previous lecture I have explained the conditions that are favorable for crystallization to occur. But before I proceed with the discussion on the stages in crystallization, let me just recap very quickly. First, in order to form a crystal, the liquid phase must exceed the equilibrium condition and become super saturated for a solution, or become super cool for a milk, such as the chocolate milk. So for example, if you look at this solubility curve for sucrose, which I have explained in detail in the previous lecture, so we have the equilibrium solubility curve here. So what we want to achieve to create the favorable condition for crystallization is the supersaturation state. So we want to be at a point above this solubility line, where the solution now is in the supersaturated state, and it's ready to start the nucleation, or the first stage of the crystallization process. So how to achieve this supersaturated state? So basically we can achieve this by either cooling below the melting point of a compound. The compound can be the crystallizing species, such as water or the triglycerides in the oil, or by somehow producing a concentration in a solution greater than the solubility concentration, meaning that we have to be above this line, because any line on this solubility curve is the equilibrium solubility. So we have to create a condition where we can go above this solubility line, which means that we have to go to the supersaturated state. So on this slide now we will discuss how to achieve the supersaturation state for a solution. So for this purpose, I will use this solubility diagram to show the different path how we can achieve the supersaturation. Let's say we want to prepare a sugar solution, and we start, say, somewhere in at point A here in the diagram. So this is undersaturated solution, but in the first way or the first method to create supersaturation, we start with a solvent. In this case, let's say we use water as a solvent, and we heat up the solvent to a high temperature. So suppose we are now at this point, quite high temperature, and then we dissolve the sugar in here. So we have what we have now is the sugar at high concentration, at high temperature. Then after that we can cool down this solution, or the sugar solution, to a lower temperature. So when we cool down the solution to a lower temperature, if you still remember, at lower temperature the solubility of the solute also is lower. So what happens here, at this point we have high sugar concentration because the temperature is high and the solubility is higher. When we cool it down to lower temperature, now we have excess of solutes, which will now need to be crystallized out. So what we have at this point now is actually a super saturated solution, and you can see that when by lowering the temperature, we actually cross the solubility line and we go into the supersaturated state. So that is the first way to create a supersaturation. The second method to create supersaturation is the one that is commonly used in a commercial or in the industry, for example in the production of sugar. So the second method is actually by evaporating the solvent from the solution. So let's say we start with at point A again here. So we have an undersaturated solution. So now we heat up the solution. For example, we can do this in the evaporator under vacuum. So heating actually would cause the solvent or the water in the solution to evaporate, and as a result it will increase the concentration of the solute. So it will increase the concentration from point A, and it will cross the solubility line into the super saturated state. It can be at this point, or it can be at any point above the solubility line. So now we have a super saturated solution. And the third method is by adding a second solvent in which the solute is insoluble or has a lower solubility. And this method is not actually very common in food processing or food industry, but the principle is when we add a second solvent and the solute in the solution is insoluble in this second solvent, so what happens, it will actually shift this solubility line, the red line here. We will shift the solubility line to a lower solubility value. So for example, if we have the solution at point A again here, which originally it is in the undersaturated state, when we add the second solvent, it can be alcohol, ethanol for example, and now the solubility curve is shifted down. So what we have basically now, the solution becomes super saturated state. So once the solution or the melt has been super saturated or super cool, there is a thermodynamic driving force for crystallization now. That is, the molecules in the liquid state would rearrange and eventually form into a stable cluster. So if I can say, I can draw, for example, we have originally the solution, the solute in the random order. So when the thermodynamic driving force is suitable or available, the solids will arrange into ordered arrangement into a crystalline lattice. So this process is called nucleation, which is the first step in the crystallization process. So next I will explain in more detail about the process of nucleation. Okay, now we will discuss the different types of nucleation. The formation of crystal nucleus during nucleation can occur actually by a different mechanism. One is called a primary nucleation, and the other one is called secondary nucleation. The primary nucleation refers to the formation of crystal nuclei from a solution that contain no pre-existing crystal, and it occurs both through the homogeneous and heterogeneous mechanism. The homogeneous nucleation is the formation of nuclei within a homogeneous fluid. What it means here, let's say we have, say, a solution in a vessel or in a container, and we have a solute, okay, but we have the solutes such as, for example, sugar, but there is only a solute there without anything else. So in this case, the type of nucleation that can occur here is called homogeneous, primary homogeneous nucleation. The homogeneous nucleation is actually very rarely occurs in the practical food processing condition. On the other hand, we have in food industry, commonly we have the heterogeneous nucleation, which is initiated by contact with foreign particles or the surface in the solution. Because in food processing, usually you will find the dust or other particles, or there are other foreign matters or foreign particles that can be present in the solution, and this would provide a nucleating sites for the nucleus to form, and subsequently it will induce the nuclei formation at much lower supersaturations or subcooling than those required for homogeneous nucleation. So for example, in heterogeneous nucleation, suppose we have again a solution in a vessel or in a container, and we have the solutes to be crystallized, but we also have maybe dirts or other particles, and this actually can serve as a nucleating site for the new nucleus to form. Sometimes actually even the surface of this container, because of the rough surface or the pitted surface on the vessel, this itself can actually provide the nucleating site for the new crystal to form. Okay, so this is the heterogeneous, primary heterogeneous nucleation. On the other hand, the secondary nucleation refers to the formation of crystal nuclei due to the presence of existing crystal. So there is already some probably a crystal in a solution that can serve as a new nucleus. If you recall that in the metastable zone, the spontaneous heterogeneous nucleation does not occur for reasonably long times because there is no new nuclei will form spontaneously. But under certain conditions, under certain temperature and concentration within this region, new nuclei may be formed due to the presence of existing nuclei. In the previous slide, I mentioned that the secondary nucleation refers to the formation of crystal nuclei due to the presence of existing crystals. But the question is, where do these new nuclei come from? The new nuclei are generated either by contact between crystal or between the crystal and the wall of the vessel, or the contact between the stirrer and the crystal in the solution or in the agitated tank. This kind of secondary nucleation, or the mechanism, is known as the contact secondary nucleation. There is another way how the new nuclei can form. For example, during the agitation in the crystallization vessel, sufficient fluid shear may cause small irregularities or small surface irregularities on the crystal to be sheared off and dispersed into a solution, and they will now serve as a new nucleating site where they will grow further to become stable nuclei. So what is the implication of contact secondary nucleation in the food processing? The importance of contact secondary nucleation in the food industry or in the food processing is probably greatest in those systems where crystallization is controlled for a separation of certain material. For example, in the refining of sugars, in the freeze concentration of fluid foods, for example juice, and in the fractionation of fat. In sugar refining, for example, operation of sucrose crystallizer, shown in this picture, is carefully controlled to limit any secondary nucleation, because this would result in a crystalline product with size distribution that leads to inefficient filtration. Fats are also believed to exhibit secondary nucleation, so usually the agitation during the crystallization process is kept to a minimum to prevent a secondary nucleation, because this can also lead to a more difficult separation or less efficient filtration. On this slide, we will discuss about the rate of nucleation, and I have two diagrams here. One is the nucleation rate curve as a function of a driving force, and another diagram here is the solubility curve, which I think you are very familiar now. But first, let us define the meaning of the rate of nucleation. The rate of nucleation can be defined as a number of nuclei formed per unit volume and time, and in the solution it depends on the supersaturation and also the temperature. For many food systems, the nucleation rate for a solution of constant concentration goes through a maximum as the temperature decreases. In the vicinity of point A here in this diagram, the rate of spontaneous nucleation is relatively low since the driving force is still quite small. So to understand this phenomenon, let us refer to this solubility diagram. So let's say that we are here at the starting point here. So this is in the supersaturated state, but it is at a higher temperature, and the point here is not far from the solubility line here. So the degree of supersaturation also is quite small. So what happens when we decrease the temperature? So as we decrease the temperature in this direction, okay, so the supersaturation of the solution increases from two mechanisms. First, by lowering the temperature itself, it will increase the driving force of the nucleation. However, by lowering the temperature also in general, increases the supersaturation through the depression in the solubility concentration. So you can see here. Thus, the driving force for crystallization increases rapidly as temperature is decreased. So as you can see here, as we decrease the temperature, the driving force increase due to the effect of the temperature, where the kinetic energy is taken out, the movement of the solids become slower. So the formation of the nucleus also will increase, and also the lowering temperature also will increase the degree of supersaturation, and therefore increase the nucleation rate very rapidly. So the increase in the nucleation rate between point A and point B here is very rapid until the maximum point, and at this point there is actually increase in the viscosity of the system at the same time, and when the viscosity of the system become very high, the nucleation rate also will start to decrease, because the diffusion of the solids to form the crystal lattice in the nucleation stage would be hindered or would be slowed down. So we can actually observe the decrease in the nucleation rate to the point C here. This diagram also shows a comparison of the relative rates of nucleation for homogeneous versus the heterogeneous nucleation. So as you can see, the homogeneous nucleation does not begin until some reasonably high driving force or a critical the critical supersaturation is attained. Beyond this point, however, the nucleation rate increased dramatically with small increases in the driving force. On the other hand, the heterogeneous nucleation occurs initially at a lower supersaturation driving force, and it will increase rather slowly compared to the homogeneous nucleation. Now let's discuss some factors which can affect the rate of nucleation. The first one that The first factor that we want to discuss here is the supersaturation. The nucleation rate usually goes through a substantial increase as supersaturation increases through some critical point. And below this critical supersaturation, nucleation rate is very low, whereas above this critical point, nucleation rate is very high. So for example, if we have a point here on the solubility curve, and we have another point here on the solubility curve, so obviously if we look at this point in relation to the solubility curve here and here, so obviously at this point the degree of supersaturation is much higher, and therefore we can get the very high nucleation rate to occur. On the other hand, let's say we have a point here on the solubility curve at a certain temperature, and another point here. So again, this point here means that we have a higher degree of supersaturation compared to this point here. So in this case, the rate of nucleation at this point would be much higher than this point. The next factor which can affect nucleation is the temperature. Temperature is closely related to driving force in both a solution and also a melt system. In a melt system, lowering the temperature below the melting point or below the metastability zone induces a rapid onset of nucleation. The nucleation rate increases rapidly with a slight decrease in the temperature in the region near the melting point for melt, or near the solubility for a solution. So for example, if we start from this point in the solubility curve here, when we cool down the temperature, so the system now will become goes to the supersaturated state very easily or very quickly, and this will increase the driving force for the nucleation compared to if we start at this point, which is far from the melting point or far from the solubility equilibrium solubility of the solution. So we need to reduce the temperature to a longer, or it will take a longer time to get to the supersaturated state, and therefore the rate of nucleation also will increase more slowly compared to this point. So as we reduce the temperature, the rate of nucleation will increase up to a maximum point. So at some point, the viscosity of the system will become very high, and it approach the glass transition temperature, where at this or near this glass transition temperature, the viscosity is very high, and it will reduce or limit the diffusion of the molecules, and therefore the effect actually it will decrease the nucleation rate. So at point C, the driving force is for the nucleation is very small as point A, but at point C, the reason for low driving force is because of the high viscosity, which limit the diffusion of the molecules in the system. Another factor which affects nucleation is viscosity. The viscosity increase due to two factors. One is by lowering the temperature. There's always an inverse relationship. When we decrease the temperature, the viscosity would increase because of the decrease in the diffusivity of the molecules. Another factor is the increase in concentration also will increase the viscosity. For example, if we start from this point, and we remove the solvent by using evaporation. So this will increase the concentration of the solutes, and therefore it will also increase the viscosity. So if the viscosity become very high, the system will approach the glass transition temperature, where at this glass transition temperature, close to this temperature, the viscosity is very high. It can be around 10 to the 9 or 10 to the 11 or 12 pascal a second. So under this very high viscosity condition, the diffusivity of the solutes would be very slow, and this can affect also the rate of heat transfer, which consequently can influence the nucleation process. The diffusion or the viscosity of the system can also be affected by addition of hydrocolloids such as carrageenan. For example, when we have the carrageenan in the ice cream mix, so the carrageenan would give a high viscosity, which also would decrease the rate of nucleation. Another factors which can affect nucleation is the cooling rate. Generally, a rapid rate of cooling would lead to increase in the driving force for nucleation and increase the nucleation rate. For example, from point A here to point B. And a rapid rate of cooling also would lead to nucleation at a lower temperature compared to slow cooling. To understand the effect of cooling rate, we must understand the fact that when we cool down the solution, say at this temperature here, and we cool it down to this temperature, at this temperature, at higher temperature, the solubility of the solutes is higher, meaning that the solution can take more solutes. And when we reduce the temperature, and we know that the solubility of solutes at lower temperature is also lower than at high temperature. Okay, so by lowering the temperature, it will also reduce the solubility of the solutes. And the faster the rate of cooling, the nucleation rate also will increase very rapidly compared to if we cool down the solution more slowly. So the rate of cooling to a supersaturated state can be extremely important process parameter in some systems. In some products, it is desirable that nucleation of all crystals occurs at approximately the same time, so that all nuclei will grow to be crystals of about the same size. So we will end up with a narrow crystal size distribution having more or less the same size. And usually by using rapid cooling, we can get a small size crystal of having more or less the same size. And in a slow rate of cooling, some nuclei will form early in the process and they will grow larger than the majority of crystals formed later in the process. And these large crystals can have a negative impact on product quality. In a product such as fondant, by the way, fondant is a candy paste made from a cooked sugar syrup or from a powdered sugar-based mixture. So in this fondant, the rapid cooling of the sugar mass in the processing is desired because we want to form crystals at the same time, and all these crystals will grow also at the same time to form homogeneous and uniform crystal size with narrow size distribution. If some crystals form during cooling prior to the main nucleation event, these crystals will be significantly larger than the average, and the fondant with coarse texture will result. Therefore, the cooling rate in fondant processing should be rapid enough that no crystals would form until the main event triggered by agitation in the beating in the vessel. If cooling of the sugar mass is slow, nucleation may potentially occur at a higher temperature than desired, and continue as temperature is lowered. As a consequence, a wider distribution of crystal sizes is then obtained. The next factor which affect the rate of nucleation is the agitation rate. The agitation is widely considered as a factor that can promote the rate of nucleation. In general, greater agitation or energy input into a supersaturated solution would accelerate the onset of nucleation, and it is thought to increase the rate of nuclei production. Also, increased agitation rate is thought to decrease the extent of the metastable zone. If you remember, the metastable zone is not actually a fixed zone. So in the metastable zone, we cannot get or we don't get a spontaneous nucleation. But by increasing the agitation rate, we can reduce the area of this metastable zone. Maybe we can make it smaller, okay, like this, so that we can get into the labile zone more quickly or more easily. Also, in the manufacture effect of agitation in the manufacture of fondant, a highly supersaturated sugar syrup is exposed to high agitation levels to promote the maximum formation of nuclei. If the highly concentrated syrup is not agitated, nucleation would occur very slowly and the product does not have the many crystals desired for the smooth texture. The final factor that can affect the nucleation is the additives or the impurities. Ingredients that influence crystallization may be specifically added or intentionally added to the formulation, or they can also present as impurities in other ingredients. Sometimes other ingredients are added to foods to help control crystallization. For example, in a product like hard candy, we can add glucose syrup as an ingredient to slow down nucleation of sucrose. Addition of seed materials is actually an example where additive can promote crystallization. Okay, before we end this lecture on nucleation, I have a few questions for you to think or to ponder upon. Try to answer this question to test your understanding of this topic on nucleation. So the first question here, can spontaneous nucleation occurs in metastable zone? Next, what happens when seed crystals are added in metastable zone? The third, why cooling the solution increases the thermodynamic driving force for nucleation? And the fourth, explain how rapid cooling of supersaturated solution results in narrow crystal size distribution. And the last one, in sugar refining and fat fractionation, the agitation is controlled carefully to minimize secondary nucleation. Why is this necessary? So that's all for now, and I hope you can do and read other references to get and to learn more and understand about the nucleation process and in the crystallization process. Bye for now.